In early 2023, a high-altitude balloon from China crossed U.S. airspace, traversing the continent before military aircraft intercepted it off the coast of South Carolina. U.S. defense officials tracked the object for days before ordering its destruction, focusing the immediate national conversation on border security and the tactical response. The event highlighted a specific, unresolved problem in the global governance of altitude: the gap between the physical reach of modern surveillance and the legal definitions of where sovereign airspace actually ends. This altitude band, positioned above the ceiling of traditional civil aviation but below the threshold of orbital mechanics, is known as mesospace or near space. Operating vehicles in this region cost significantly less than launching orbital satellites, while allowing payloads to gather higher resolution imagery and data because of their close proximity to the Earth. However, despite the technological capacity to reach it, there is no formally agreed-upon international boundary defining where sovereign airspace ends and outer space begins. Legally, this renders near space a domain governed by the principle of res communis omnium, a Latin term meaning belonging to all for the use of all. It shares the same legal status as the high seas. Yet any vehicle operating in this physical void requires a constant stream of telemetry, navigation, and command data. That data travels via the electromagnetic spectrum, a domain bound by rigid, highly enforced international law. To understand how these platforms operate, we must look at them through a jurisdictional matrix. On the y-axis is the physical altitude, and on the x-axis is the governance of the electromagnetic spectrum. High-altitude platforms occupy a contradictory position. They fly through a physical void lacking distinct borders, while simultaneously relying on a digital grid mapped down to the kilohertz. The International Civil Aviation Organization, or ICAO, formally recognizes each nation's sovereign right to control the airspace above its territory. For the United States, that active control effectively tops out at 60,000 feet. Below that ceiling, the Federal Aviation Administration maintains domain awareness. They track over 45,000 flights navigating through 29 million square miles of domestic airspace every day. This surveillance effort relies heavily on cooperative tracking technologies. Powered aircraft operating above 10,000 feet must be equipped with Automatic Dependent Surveillance Broadcast, or ADSB, a system that continuously transmits GPS location data. Flights operating under instrument flight rules file detailed flight plans and receive unique transponder codes. Visual flight rules allow pilots more freedom, requiring only generic transponder codes and two-way radio communication when nearing busy or high-altitude sectors. The system breaks down when applied to unpiloted balloons and certain drones. Current regulations do not require high-altitude free balloons to carry ADSB or active radar transponders. Without these cooperative signals, air traffic controllers must rely on primary radar returns, the physical bounce of a radar wave off an object. High-altitude balloons, built from thin, non-reflective materials, return notoriously weak primary signals. By the time an object ascends past 60,000 feet, it exits the primary zone of strict cooperative FAA control. Above this line, the legal framework dissolves into ambiguity. Operators must request special clearance to transit the controlled airspace to get there, but the destination itself lacks binding operational procedures. Operating commercial vehicles in an extreme, unregulated environment carries established risks. In 2023, the submersible Titan imploded during a descent to the Titanic wreckage. The depths of the North Atlantic, much like near space, exist under the legal doctrine of res communis omnium. Because the high seas belong to no single nation, the jurisdiction over vessel safety is loosely enforced. The Titan utilized a carbon fiber pressure vessel that had never been certified by an independent, officially recognized marine classification society. It descended into an extreme environment, relying entirely on the manufacturer's internal testing. Suborbital vehicles and commercial high-altitude drones currently lack the standardized safety frameworks or mandatory certifications required for traditional aviation.
Without definitive delimitation and safety standards, the commercialization of near space mirrors the early, unregulated stages of deep-sea exploration, where the absence of oversight creates persistent uncertainty for both operators and the general public. The ambiguity of altitude governance contrasts with the second axis of our matrix, the electromagnetic spectrum. Every transmission to and from a high-altitude platform is governed by the International Telecommunication Union radio regulations, a binding international treaty adopted by UN member states. This diagram shows the radioelectric spectrum, the lower portion of the broader electromagnetic spectrum, encompassing frequencies below 3,000 GHz. The ITU treats this bandwidth as a finite, non-replicable natural resource. To prevent signal collision, the ITU separates permission into two distinct layers. An allocation grants a specific frequency band to a type of radio communication service globally. An assignment is the specific authorization given by a local administration for a single station to use that frequency. This table shows the ITU table of frequency allocations, the master blueprint dividing the spectrum among different services across specific geographic regions. Notice the services written in capital letters, such as Maritime Mobile. These represent primary categories. A primary allocation gives the service priority. Stations operating under a primary service are guaranteed protection from harmful interference. Conversely, services listed in standard case, like Aeronautical Mobile in the third column, belong to the secondary category. Secondary stations operate under a strict rule of non-interference and non-protection. They cannot cause interference to primary stations, and they cannot claim protection if a primary station's signal disrupts their own. The system accommodates specific national interests through footnotes. A country can insert a footnote to alter a frequency's allocation category or add a new service within its own borders, provided it does not disrupt the wider network. This map illustrates how the ITU enforces this framework geographically, dividing the globe into three major administrative regions to coordinate frequencies on a massive scale. While the physical altitude of mesospace remains unmapped by international treaty, the radio waves passing through it occupy a strictly classified and shared international grid. Consider the high-altitude payload drifting 20 miles above the Earth. Plotted on the jurisdictional matrix, the platform sits on the unregulated y-axis of physical space, but is locked into a rigidly allocated x-axis of radio spectrum. An operator can physically launch a balloon into the stratosphere without filing an instrument flight plan. But that same operator cannot legally transmit weather data or imagery back to the ground without a proper ITU frequency assignment. The necessary communication link between the Earth station and the space station acts as a de facto regulatory tether. The physical vehicle escapes domestic airspace, but its data relies on a governed resource. This operational loophole intersects with national defense frameworks, like the Air Defense Identification Zones monitored by NORAD, which require position reports and transponder use from approaching aircraft. Military developers recognize this gray zone. Hypersonic gliders and advanced surveillance platforms are increasingly designed to operate in near space, leveraging the lack of physical delimitation while using the spectrum to transmit intelligence. As the cost of launching suborbital technology drops, a patchwork system relying on domestic defense zones and ITU spectrum assignments cannot safely manage the impending surge of commercial traffic. To stabilize this domain, the international community must draft physical delimitation laws. The success of the ITU radio regulations proves that nations can agree to share and regulate a valuable, finite resource. Establishing sovereignty and safety in the 21st century demands completing the jurisdictional matrix. True control of the sky requires the exact same governance we already apply to the invisible spectrum.